Two philosophers are conversing on the topic of truth-conditional semantics, giving an introduction to how it started and how to convert natural language into a meta-language. So let's dive right in.
Hey, it's been a while since I've learned about truth conditional semantics and would love to have your inputs on the topic.
Okay, let's begin by talking about how it came into play. I have a video which was shot long ago about the news when Alfred Tursky propagated his theory of truth and was talking to a philosopher. Let's play it.
Breaking news! A modern approach to cognitive semantics, known as truth conditional semantics, is emerging. It uses the best of both worlds, both mathematics and cognitive semantics. The ideas relate to what meaning, truth, and reality are, as well as how meaning can be derived from a formal language known as metalanguage, which is based on logic or reasoning. Let's find out how philosophers are understanding this concept of truth.
Alfred, for centuries, philosophers have connected truth with reality, believing that a statement is true if it matches what's actually happening in the world. The idea is known as the correspondence theory of the truth. Do you agree with this view?
Yes, but I take it a bit further. I believe that a statement's truth is closely tied to its meaning. If a statement is true because it matches something real, then that match defines its meaning. For example, if you look at anything, you can determine whether it is a dog or not. You can take a dog to be a black box, and the output would be a true or false value. For example, when you see this image, you see that it is a dog, and hence output is true, whereas you know that this is not a dog and a fish, and hence the output value is false. This means that you know the meaning of the word dog because it matches with something in the real world that you know. Certain conditions have to be met in order for the expression to be true.
Yeah. So you are saying that a sentence meaning comes from how well it matches up with what's really going on.
Exactly.
Yeah. Can you give an example of a sentence which need not be true?
Let's say I said that the last person who came to talk to me was wearing a white t shirt. You know what this means, but you do not know if it is true or not in the current context. There is a problem when we try to apply this to everyday languages like English. These languages often define words using other words from the same language, which makes things a bit messy.
Okay. Can you explain what you mean by that?
Sure, think about how we define words. For example, we might say that a bachelor is an unmarried male adult. But notice that we are using English to explain English. It's like a loop that does not give us a clear objective definition.
I see. Because natural languages define words using their own terms, they can't give us a straightforward way to understand meaning objectively. I have heard that such self-defined languages are usually called closed languages.
Yes, that's true. That is why I suggest translating things from an everyday language to a more precise language, such as a meta language, which I like to call predicate calculus. Predicate calculus helps us to provide a logic based meta language for capturing the invariant or context independent aspects of meaning. According to this view, predicate calculus or any similar logical language provides a means of capturing meaning in a way that it is objective, precisely stated, free from any ambiguity, and universal in the sense that it can be applied to any natural language.
Predicate calculus, how does that help?
Well, it's like a tool that helps us talk about meaning in a clear and universal way. It is not tied to any specific language, so it gives us a way to understand meaning without getting tangled up in the quirks of everyday speech.
So your approach aims to create a more straightforward way to analyze meaning without getting bogged down in the messiness of everyday language.
That's the idea. It's about finding a way to understand meaning that works for everyone, regardless of the language that they speak.
That's lovely. I hope future generations understand the need of a meta language and learn how to translate from natural language to predicate calculus.
Thank you. That was amazing. Surely I've understood how it started, but now I actually want to learn how to convert natural language into meta language. I've read about this and would love to share what I know, but I also want your perspective on this.
Okay. Predicate calculus, the logical meta language into which truth conditional semantics translate natural language like English, contains a range of expressions. So these expressions represent the meaning represented by units of language like nouns, verbs, and adjectives by means of terms. So basically, there are two terms, kinds of terms in meta language. There are individual constants and predicates.
Constants are expressions that relate to specific entities, like James Bond or the spy, and are represented by lowercase letters of the alphabet, such as lowercase a, b, c, and so on. Predicates are expressions that represent processes expressed by verbs like eat or they can be properties expressed by adjectives like funny, or they may be roles such as expressed by nouns such as a top British spy, and relations expressed by prepositions like under.
Predicates, on the other hand, are represented by uppercase letters of the alphabet like A, B, C, and so on. They can be one place predicates like funny, die, or top British spy, only require a single participant to complete their meaning. Example, James Bond is funny, or James Bond died, or James Bond is a top British spy.
But I can also think of other sentences like Kasparov appreciates Gukesh for the win, or Rajasthan Royals crushed Mumbai Indians. Let us see a short replay.
Correct. Now comes the best part. When constants and predicates are combined, the results in a form. This results in a formula. For example, Fred sings. So it can be represented as S of F. By convention, the predicate occurs first in the predicate calculus formula. So the translation does not reflect the word of order of English. So let's take a two-place predicate. Will slapped Chris. So here we will represent this as S of W comma C because the relative order of the constant is important as S of C comma W will mean Chris slapped Will.
I can think of some more unique words in sentences like Will slapped Chris and Chris slapped Will. These clauses are connected by natural language connectives such as and, or, but, and so on. In Will slapped Chris and Chris slapped Will, but not John, the negation word not is an operator, an expression that takes scope over some part of the sentence and affects its meaning. Natural language expressions like all, every, and some are also operators. These words are quantifiers and they help quantify different words in the sentence.
Let's move on to logical operators. Here we can see the reference table on the slides which shows an overview of them. So here we can see there is every connective and their syntax which can be interpreted in English and the operators where their syntax is shown, and we can also interpret them in English as quantifiers. So
I've understood the basics of this conversion. Now I really want to put it to practical use and follow steps in order to convert natural language into meta language. Now let's touch upon it.
So basically there are four main steps in this conversion. First step, assigning values. Giving the predicate calculus symbols a semantic interpretation in the first step. We determine the semantic significance of the symbols. For example, predicates expressed by eat and love are represented by E, L, and so on. And constant expressed by proper nouns like Jane and Tom are represented by small j and T and so on. So let's consider our earlier sentence, Will slap Chris. So here we will assign small w as Will and small c as Chris.
The second step should be establishing a model of the world, correct? The second step is the establishment of some model on the world against which the symbols in the meta language can be matched. This is usually depicted using set theory or Venn diagrams. For example, in a model of the world where all women love chocolates, the sentence all women love chocolate would be true. However, in a model where only a subset of women love chocolate, another subset loves chips and another subset loves both, as seen in the slides, we would say that the earlier sentence, all women love chocolate, is false. Since symbols are matched with a model of the world, this type of approach is also known as model theoretic semantics.
Yeah. In third step, we having matching formula with model. This is also known as denotation. For example, in the sentence, all women love chocolate, the predicate love represents a relationship between the set of all entities described as women and the set of all entities described as chocolate. Once this matching operation has taken place, then the truth value of the sentence can be calculated. The domain in our sentence may consist of multiple people: Chris, Will, Fred, John, Jane, Mary, Susan, and Tom. Within this model is a domain or subset of entities who stand in the relation expressed by the predicate slap S. So each ordered pair inside angle bracelets stands in the relevant relation. Here we can see Will, Chris is a ordered pair like the Fred and Jane and Mary and Susan.
And last but not the least, we calculate the truth values. If your formula matches the model, then the sentence is true, and if it does not, then the sentence is false. For example, S of WC, which is slapped will Chris, is equal to 1 because the pair will comma Chris is a part of the ordered set shown above. In this rule, the number 1 represents true as opposed to 0 which represents false. The rule says that will slapped Chris is true if and only if the ordered pair is a member of the set S. Since the set S shown in the previous slide contains the ordered pair in the model, the sentence here is true.
Yeah, amazing. Now let's see a more complex sentence. Here we can see every pupil sat an exam. So here sat is represented by capital S and pupil is represented by capital P. So the pupil is not specifically defined and can be a variable X. So here exam is defined by small e. So we know that if a variable X person is a pupil, then he sat in an exam. So here we can represent it as p of x gives s of x comma e. That means for every x that is a pupil, he will be sat in an exam. So this is the meaning of this. And next we will on next step we will see that for all pupils which are for all people who are pupils, they are sat in an exam. So this is represented by the following equation. I think you have a fair idea now of truth how truth semantics works.
Yes, I surely do. But